So let's just start off with the basic circuit. The circuit has a source of is a source of EMF, and let's look at a resistor in this circuit. This circuit has a current going through it, which I will label as I, and I'm drawing the current in the clockwise direction because current goes from high potential of the positive terminal of the battery to low potential of the negative terminal of the battery. I'll also indicate a couple of nodes here. So this node at the negative terminal of the battery and this node at the positive terminal of the battery. So resistors work by resisting the flow of charge.
Right.
If it wasn't for resistors, or if it wasn't for resistance in a circuit, charge would flow freely. It flow quickly. If you attach just a simple wire though to two ends of a battery, and let's just maybe draw this. I would not recommend trying this at home, or if you do, be very careful when you try it. So let's say we have a 9-volt battery here.
Mhm.
If I just took a wire and attached it to both terminals of that 9-volt battery, well, this wire is very low in resistance. Let's look at the current that could be generated by this wire. So we know from Ohm's law that the potential difference, this will be the 9 volts, is equal to the product of the current times the resistance in whatever circuit you have. So if I have a very low resistive wire, so if R is very, very small, that means current is big. So as R goes to 0, so in other words, as the resistance in our wire goes to 0, the current goes to infinity. Very huge. What will happen though is that wire, because there will be such a large current going through that wire,
Yeah.
and because the wire does have resistance, the wire is going to heat up very quickly. If you were to touch it, even after a few seconds, it may be too hot to touch. Now, if we were to just take a segment of the wire and were to look at the atoms that make up the wire, and we will say we have the high potential side here, the low potential side here, and let's follow the journey of a positive charge in this wire. So there's our positive charge. Now, positive charges move from high to low potential. So what happens is as this positive charge moves from high to low, it has numerous collisions. And you might remember from physics 4A that these collisions, largely inelastic, will cause a transfer of energy from kinetic energy to thermal energy.
Yeah.
Do you remember that? We're like, go ahead.
Yeah, kinetic energy to thermal energy.
Yeah. A lot of that kinetic energy goes to thermal energy. And you experience that anytime you rub your hands together for warmth, the resistance in the palms of your hands as you apply kinetic energy between the palms of your hands, the resistive forces will try to slow you down. And those resistive forces generate thermal energy. And if I didn't continue supplying energy to rub my hands together, my hands would eventually slow down and stop. Or you could imagine maybe sliding a block across a floor. If you had a block and you slide it across the floor, you let it go, it'll eventually slow down and stop because that kinetic energy gets transformed into thermal energy. Same thing happens in wire. So this example of this 9 volt with the single wire attached, very low in resistance, the current gets really, really large. And remember, current is the time derivative of charge. And we could measure it by looking at the number of charges that cross a point on this cross section.
Hmm.
So if we have a large current, then we would be having a large number of particles crossing that point per second. Smaller current would be fewer particles. But if we have a lot of particles crossing that cross section,
Hmm.
all of the collisions will generate heat. So, in other words, the resistive forces in that wire, you can think of it like electrical friction. Those resistive forces will dissipate energy in the form of heat. And we could determine the rate at which that energy is dissipated in the form of heat. And that rate is called power. Power, if we remember from Physics 4a, power was defined as the time derivative of work. So work per unit time.
Yeah.
If I do 50 joules of work per second, then I would have a power of 50 watts. Or 100 joules per second is a power of 100 watts. Well, if we put this in the context of circuits, remember, change of potential energy is equal to minus the work done, on a particle. And we can also say that a charge times the change of potential is equal to the change of potential energy. And this is just equal to minus the work done. So we could say that power then is equal to minus the transfer of potential energy per unit time. And actually, let's look at the magnitude of this power. So this will be du dt, which is the time derivative of the product of charge and electric potential. So if we take our circuit with the resistor attached, we have point A, we have point B, there's the current going through. Because this EMF is a constant source of potential difference, we could say that in this derivative for power, the delta V, the potential difference, is a constant. It comes outside of that derivative.
Mhm.
And we are left with the derivative of charge with respect to time. But remember, we defined the rate of change of charge with respect to time as being the current in our circuit. So what this means is this expression dq dt,
Mhm.
that is just I. So this is saying the power, the rate at which energy is transformed in our circuit is equal to the product of current and the potential difference. This is for any electrical component. And this expression right here reveals the rate at which electrical components consume energy. This rate is based off of the current going through that electrical component and the potential difference of that electrical component. So, this expression for power, the rate at which electrical components consume energy, is the product of current and potential difference. So, the greater the current in the circuit, the greater the rate at which our electrical components consume energy, or the higher the potential difference, the greater the rate in which it consumes energy. Now, remember, power is measured in watts. So, in a watt is a joule per second. So, it tells us how fast energy is being transformed or transferred in our circuit.